Hi, welcome to another Sedra Smith series on analysis of a diff amp. I'm going to try and derive the differential gain of a diff amp. But before I do that, I wanted to talk a little bit of some of the characteristics, things about the diff amp. Okay, typically you're going to have matching inputs. Let me label this as M1, M2. Typically these will be the input and you want to match. Okay, what do I mean by that? Okay, it means that you want the same width and you want the same length. Okay, and second is you'll have your loads. In this case we'll label this 3 and 4, and you want your active loads to also be matched. Basically the width the same, the width and the length the same. Okay, now if you look at your active loads, those are composed, and let me draw a line in between here. These are your P channels, and everything below is your N channels. Okay, and if we look at the P channels, you should identify that the gate is connected to the drain. So in some of the books they're referred as a diode connected MOSFET. Okay, so I'm going to go ahead and refer to it as that, or you can also say that it's a drain or a gate drain connected MOSFET. Okay, and whenever you see a diode connected MOSFET, if you see the gate also connected to another one, then those two form a mirror. Okay, and if they're the same size, and if you recall, if they have the same size, whatever current flows through here also is reflected, shows through here. Okay, so that's another reason that you want M3 and M4 to be matched. That way the currents are the same. Okay, and then the inputs are your N channels. Okay, and I went ahead and labeled this as positive, and this is Vn, the negative. And a question that you may ask, well, how do you know which is the input and which is the output? Okay, well, what you do is you can start whatever node. Let's say we start here, and we'll assume that we start with a positive. Okay, and since it's a common source, if you put a positive here, you're going to get a negative here. That's at the output. So a positive, you get a positive here and you get a negative here. That means that's the wrong polarity. It's not P. It's not a positive node, it's a negative node. Now if you come over here and you do the same thing, you start with a positive, you're going to have an inversion, so you're going to get a negative through here. Okay, so you get a negative here, and then you have another inversion, so it's positive. So since this is positive and you start with a positive, then this is your positive node. So you may have different stages. You may have, this is a one stage. Typically the minimum that you can traditional op-amps will have another second stage. You can start from the output and go back, or you can start from the input and go back and see what you get. But anyway, that's the way you identify which is your positive node and which is your negative node. Okay. Another critical thing to remember is that when you have a diff amp, you have a current source. This is your current source. And it sets the bias current that's going to actually flow. And this will go through a current mirror typically. So forth. Okay. And if these two are matched, then this I bias actually gets divided. Okay. But there's a caveat. Okay. They're divided if VP and VN are equal or are the same voltage. Okay, so as long as you can have a VDD here, VDD, you still have the same bias or anywhere in between. So basically, as long as they're the same, you're gonna have that. Now, if you put a little wiggle here, or let's pretend that, let's say they're biased at 2 volts, both. You should have half the current flowing through both of these. Okay, but let's say we slightly raise it up, let's say to 2.2 volts, and then have the negative remain at 2. Okay, what does it do? Well, as you raise this up, you're increasing VGS. Okay, and remember, if you look at your diode equation, or not the diode, but the saturation equation that we use, when this goes up, ID goes up. So this current actually increases. Okay, it increases. And if it increases, that means that this current that is supplied by M4 also increases. Okay, and what happens to this current? Originally there was equal, because it increased over here. It actually robbed some of this current that was coming from here, so this current decreases. Okay, so basically it's kind of like you can think of it as a seesaw. Okay, a seesaw that perfectly blends. If you raise the current or the voltage on one, then you have a little imbalance. Hang on. Just like in a seesaw, you add weight on one side, or actually you increase the current on one, the current goes up in this, and then it increases here. Well, the current is going to decrease on one side of the MOSFET. So in this case, this would be M2, this would be N1. Okay, but the same token, you can do the same thing here. You can set this at 2 volts, raise this to 2.2. Okay, if you raise it to 2.2, then the current is going to go up. Okay, this current will go down, and since it goes down, this goes down, this goes down, and so forth. So then you have, it swings the opposite. and 2 will have an increase and you'll have a decrease on that. Okay, so it's kind of like a balancing act. Okay, and I guess that's the best analogy that example that I can use, kind of like a seesaw. May not be the perfect, but that's how I tend to think of things, or at least in this. Now, to do a analysis, or at least try to calculate the gain, you have to do a little bit of a hand waving. Okay, actually there is a derivation to prove this, what I'm about to say, but it's a long, treacherous derivation, and I don't care to go through it right now. But basically, the hand waving comment that I'm going to say is this: if you're in small signal mode, and we're going to do a small signal analysis. If you put a little wiggle here, positive wiggle, and if you have a differential, you're actually going to get a negative wiggle. This will be 0, this will go into the negative direction, and this will be, say that's 0, this would be positive. But the same token, if you swing negative, then this will swing positive. And what I'm saying is that that the voltage at the input, they're going to reverse if you have a differential. Okay. Now, what does that do? Well, because one goes up and the other goes down, and vice versa, the voltage at this node stays the same. Okay, and it can be considered a virtual growl. Okay, so by that statement, you can assume that that node is growl. Okay, and this is a very important concept because it helps in the derivation. Okay, so now that we have that, we can go ahead and do a small signal analysis. Okay, now in this case, since we've been practicing how to derive impedances and gains, you can do this almost by inspection. Okay, and in the end, you end up practicing your skills on how to derive, so you can eventually do things almost by inspection. Okay, so here's an example, although it's a very simple example, but nevertheless it's one. We're going to get the gain from VP to A, and then from A to V out. Okay, so we'll do that. So VA to VP. Okay, so when you come in here and you put a, let's say, and I'll name it VD, and since it's a differential mode, that's connected to ground, so that means that this we can connect to ground. So basically this is connected to that side, so this is valid. Okay, so now we're ready. So if we put a signal at the gate, okay, the gain in this node the first thing you should say, okay, it's a common source, okay, you know that you're going to have negative inversion, and you're going to have a GM1, okay, so you're going to have the GM1 of 1, and then you look at the impedance looking into the drain of N1, and then looking at the drain of the diode connected of M3, okay, so then you can say that it's RO1 in parallel with 1 over GM of 3, okay. Now what about this node? Is there any impedance looking into the gate of N4, or any impedance into the gate of N5? I'll let you think about that. Okay, well, no, there's no impedance because there's a capacitor. There's a cap. Okay, there's a polysilicon that's on top of a gate oxide, and that forms a gate. So basically, the input is an open. Okay, so regarding node A, this is the only impedance. Okay, so now we're going to take the gain from A to V out. Okay, and this is a P channel. Here's your source, drain, gate, and again you look at it and you should know that it's a common source. Okay, and if you have a common source, again you're going to have a negative, and you're going to have a GM, and it's going to be a GM4. Okay, now you want to know what is the impedance looking into the drain. You're going to look into the drain of N4, and you're going to look at the drain of M2, and we should already know that it's going to be RO naught 2 in parallel with R naught 4. Okay, we're almost there. Okay, so now what we can do is we can put this together. Okay, and we'll say that it's GM1 Okay, so it's the product of those two. So you end up with V out, VP. The negatives make it a positive. Okay, so let me write it down. Okay, so it's going to be GM, oh sorry. GM1. Okay, now let's simplify. Okay, let's look at this term. Okay, you have R out, and typically you want R out, R naught 1 to be high, and the GM is typically lower, and they're in parallel. And when you have two resistors in parallel, the dominant is the lowest one. So in this case, you can simplify that to 1 over GM3. Okay, then we bring this GM here, GM4. Okay, so we're almost there. Okay, so now we made a statement earlier that M1 is equal to M2 and M3 is equal to M4. Okay, and we said they're match, basically W, L's, but we can also say that GM is match. Okay, so if we look in here, 3 and 4 match, so that means that GM4, GM3 are match, and if they're matched, that means that they're equal. Okay, so that means they cancel each other. Okay, so once you simplify it, you end up with GM1 in parallel with RO4, and that's an approximate gain, differential gain. Okay, so hopefully that give you an understanding, and not only know qualitative, in other words, how an op-amp works, or at least the currents, and how to derive the differential gain. Thank you for watching.